Welcome to my new video. Now I'm going to show you what is the exciting current in the coil. I know my previous example was very bad, sorry about that. So I know I explained it very badly and poorly, but I was really tired. So if you didn't get my last video, if you didn't understand that, no matters, it's not that important. So sorry about that. Now for example, if you have a magnetic circuit around here, don't worry about all this graphics, schematics and all of that. I'm going to explain it by details. Then this is something that you don't need to know when somebody wakes you up in 3 in the morning. You don't need to know this, all of these points, graphics and so on and so on. The most important is this and something that I will draw later on. Now, it's important to understand what is the exciting current. Now, there are two situations. One, there is no power loss in the magnetic circuit, which is ideal for us, and it doesn't really exist in real life. And with power loss, where this is with hysteresis, and we're gonna see what is the exciting current. Now, when we have a sinusoidal voltage supplied on this coil, like this, here you have a sinusoidal voltage, then you will have a sinusoidal flux, but moved 90 degrees to the right. Now, if we have a magnetic flux, sinusoidal magnetic flux, then we will have an exciting current, which is called I, and in the index this small letter flux, Greek letter for F. Now, because the BH characteristics are not linear, they are non-linear, the current, exciting current here, is not going to be linear and sinusoidal because of the BH characteristics. Now, instead of B, if you write down flux, and instead of magnetic field intensity we write down the current, then we will have this this curvature right here. I'm gonna explain all these points right now. So now first we have the induced voltage that is sinusoidal, and now we have with a black marker and with a blue marker we have the magnetic flux in this coil, which is sinusoidal but moved 90 degrees with respect to the induced voltage. Now, this red line is the exciting current, which I explained earlier, and this green interrupted line is the first fundamental current of this exciting current. So that is the first harmonic is also sinusoidal, the first harmonic, if you know Fourier series. Now, we have a nonlinear characteristic. Now this is the first point, number one. As you can see, number one here, the exciting current is 0 and the flux is 0. So that is the first point. Now here, at this point of the exciting current 2, that is 2 is numbered here. Now, at this point 2, you have a magnetic flux that is equal here on the blue line, and you have an exciting current at this number 2. So we increased the current in the positive axis, and then the magnetic flux will rise. The current rises to the number, the point 3, and then the flux also rises to the point 3. Now this is the point 3, this is the value of the exciting current, and this is the value of the magnetic flux. Current rises to its maximum amplitude, the magnetic flux has its own amplitude. So this is the amplitude. Here is the amplitude of the current, and here is the amplitude of the flux. Now the current decreases, the exciting current decreases to the number 5. Also the magnetic flux decreases to the value number 5. So number 3 and number 5 are in the same amplitude. Also the current decreases to number 6, here to the point 6. The flux decreases in its own to number 6. And then we have a point at this point 7.7. We don't have no current, exciting current. If we don't have exciting current, we won't have magnetic flux. This is only if there is no hysteresis. I am going to remind you that this is without hysteresis. Now, this was on the positive half of the cycle, and this all is on the negative. As you can see, comes to point 8, the exciting current, but in the opposite direction. And here we have the magnetic flux. Sorry, this isn't number 13, this is number 12. Now it goes to number 9, magnetic flux increases in the inverse direction, number 9. The amplitude in the other direction, opposite, is 10 here, and this is the maximum value of the magnetic flux. And now it goes, and now this decreases to 0. We have point 11, it reaches the same amplitude as 9. It goes to number 12, this exciting current, and finally at number 13, when the exciting current is 0, then the magnetic flux is 0. So no power loss we have here. The exciting current and the magnetic flux are well, pretty much are in the phase, and then you don't have any area. Here you don't have no power losses. Now this is the equivalent circuit for it. This is the inductance of the coil, magnetizing coil. This is the inductance of the magnetizing coil, and this is the fundamental exciting current, in the first harmonic of Fourier series, and this is the equivalent circuit of this here. So we only have the magnetizing inductance of this magnetic circuit or magnetic coil. Now, and here we have a phase diagram where you can see that induced voltage is this direction, and the flux is moved 90 degrees in the other direction. And as you can see, this means that the flux lags in respect to the induced voltage, and this magnetizing exciting flux, or this is called a magnetizing flux, is in phase with the magnetic flux. Now this was when we didn't have hysteresis. Now what happens when we have hysteresis? As you can see, now we have lagging. As you can see, when we increase after some few cycles, when we brought the sinusoidal voltage, we go to the steady state, and as you can see, number 1, where we have some current, we don't have any flux, and I'm going to show you that. So when we have hysteresis, we have one magnetizing current, and we have one current that is in phase with the induced voltage, and it is called the current loss current. The core loss current, sorry, not current loss current, core loss current. Now the exciting current is a little bit different. It's not in the phase with the flux, it's a little bit different. Now let me just show you all this step by step. Now I said we had the induced voltage E, which is sinusoidal waveform, as you can see with black marker. Now this black interrupted line is in the phase with that's the current of the core. So the current core loss current, which is in phase with D, and its amplitude is smaller, and it's in phase with the induced voltage E, as you can see right now. This is with these interrupted lines. Now this IM is the magnetizing current. So this current magnetizes the magnetic circuit around here, and this is the same current as this exciting current if there was no hysteresis. So this here, red interrupted lines, is actually this IF. And now this here with this green line is the exciting current that we provide to the magnetic circuit. So we will have a sinusoidal magnetic flux, which in this case is with blue line. Now, as you can see, okay, now at this point, as you can see, the magnetic flux is 0. Now, so this blue line is 0. But here at this point, this green line starts from here. Why? Because we have a value of the IC here, and the excited current is equal to the Pythagoras theorem of IC plus IM. Looking at this, so it's equal to the addition. So I flux is equal to IM plus IC. Now, as you can see, IC has its own value here. The IM is 0. Now we have a value of the exciting current, which is equal to the IC at this point. So, looking at the hysteresis loop or flux and in the current, exciting current, we have some value of the exciting current here, but we don't have no value of magnetic flux. So there is lagging. So that's hysteresis. We have lagging. Now, in this point 2, as you can see, this point 2, the flux has a value somewhere around here, and this IC over here adds up, or we summarize it with the magnetic flux here, and now we have some value over here too. Now this is the point 2, current little bit increased, and as you can see, the flux also increased. Now this is number 3. As you can see, IM plus IC, you get number 3. This is also the exciting current, and we have magnetic flux that is equal somewhere around here. So this increases, and here we have the biggest amplitude. So the biggest amplitude is then when this is 0, and this is only equal to the magnetizing current. This exciting current is equal to the magnetizing current. Then we have both amplitudes. So this is the maximum value of phi and flux. Now, as you can see, because this IC is now negative, it subtracts with this IM in this case, and then you can see that this magnetizing, exciting current decreases here, not here with this IM, because this now has a value, a negative value, and when you add this and this, you will have a curvature that is falling lower and faster than the magnetizing current of this coil. As you can see, number 5, now we decreased a little bit this current, and also the magnetic flux decreased. And at point 6 here, we have a negative value of the exciting current, but we have a positive value of the magnetic flux. That's because of the hysteresis, and that's lagging. Now here we have a negative value at 0.7 of the magnetizing flux, but we have the value 0 here of the magnetic flux, as shown right here. Now we have at point number 8, magnetic flux is here. Number 9, as you can see, it goes in the opposite direction to its amplitude. Number 10, that starts to increase. This is falling, going in this path. 11, 12, and as you can see, we came back to number 1, and number 1 and number 13 are the same. So that this is a full cycle here. This has the same value. They are at the same point, just moved for a one cycle. And you can see number 13 we have some current, but because of the lagging we don't have magnetic flux. So this is the hysteresis. So this is the core loss of the magnetic. We have a core loss current in the magnetic circuit. This IM is for the magnetizing the coil, and this is the exciting current. Now I'm just gonna show you the equivalent circuit for the exciting current with hysteresis. I'm gonna write this down. Now here we had a voltage E. This is plus minus. Now this stays the same. We have the inductance of the coil. The inductance of the circuit that we are magnetizing, L index M, and now parallel with this we have a resistor RC. This represents the resistance of the core. Here we have the inductance, we have the exciting current. Here we have the core loss current, IC. And here we have the magnetizing current. So we have power losses with hysteresis. Now this is a very important circuit. You will see a lot of this in transformers, induction motors, and synchronous machines. So this is very important to know. And how do you calculate this? You calculate this with Pythagoras theorem. So you move this to here. This is the hypotenuse, and you do the Pythagoras theorem, and you can calculate what is the amplitude of the exciting current. So with hysteresis you have some lagging, and you have core losses. So you have this equivalent circuit for the magnetic core. This is the magnetizing inductance, and this is the core losses in the this circuit, magnetic circuit. You have the exciting current. This is the core. This is the current that goes on the core losses, and this is the current that magnetizes the magnetic circuit. It magnetizes the magnetic core. Sorry. And that's it for this video. I remember this circuit. Remember this, and remember what's the exciting current. Exciting current is a current that we supply to the magnetic circuit to have a sinusoidal magnetic flux, and it's not, as you can see, it's not sinusoidal. The characteristics are non-linear, and this is very important, and this to know. You don't need to know this. This was just the representation and of the exciting current with hysteresis loss. This is most important, and this. You will see that in transformers and induction motors, that this and this, you will see these equivalent circuits. Thank you for watching, and see you in my next video.